So today we're here to talk a little bit about enterprise use of HPC in the cloud. I thought I'd just take a second and introduce myself. So I'm Jason Stowe. I'm the CEO of Cycle Computing. I have an HPC background. I out of school, worked at the Pittsburgh Supercomputing Center and the Cornell Theory Center. And I think one of the fundamental things that I believe that connecting people and through any device with up to massive computation is going to be the single most transformative part of the 21st century, period, bar none. And it doesn't matter whether you look at the Human Genome Project that finished in 2000, or the discovery of the Higgs boson, which is effectively the way in which subatomic particles acquire mass. Both of these problems required millions of hours of computation in order to make them happen, and they were placed in the hands of a very small number of researchers in order to do work that fundamentally puts humanity forward. It pushes us further along. And so it doesn't matter if you're talking about individual users, like, for example, we've done work in the past with molecular modeling. We have a company that ran a 50,000 core infrastructure on AWS. Their fundamental challenge was to be able to find drug candidates that went against a cancer target. They wanted to analyze 10 times as many molecules that might fit lock and key style into a protein affiliated with cancer using an algorithm that was 10 times more computationally intensive. And essentially, they were able to do this because they could grab $20 million of infrastructure, 50,000 cores from Amazon, do 12 and a half years of compute, and instead of it taking months on their internal environment or years, depending on whether they dedicated it or were using idle capacity, instead they did it in 3 hours at a cost of $48.28 an hour, or about $14,000 for the total run. So this is transformational. It puts it in the hands of anyone. This is a 160-person organization that for a very brief window had just as many cores as the top 3 pharma put together, and then turned it off, and the total cost was about $14,000. We're seeing the same thing in genomics as well. So the Morgridge Institute ran a 1 million hour computation. So this is 115 years in an effort to accelerate the process of identifying where a stem cell is in the process of turning into another type of cell. So they essentially compared samples with each other to try and figure out, okay, this is a knowledge base that will allow me to do a lookup and say, when I'm trying to replicate this disease in the Petri dish, this actual individual stem cell culture is on its way to being a vascular cell, or it's on its way to being a neuron cell, or it's on its way to being a cardio cell. Essentially, this lookup table process was 1,003,404 hours that was run against 78 terabytes of genomic data. And that 115-year compute was able to be done thanks to cloud HPC in about a week at a cost of about $20,000. And this is just the kind of computing power that was not available before. It's not something that individuals could use to actually run research at these scales before 2009, 2010, when we first started doing this. And we call this utility supercomputing. So today what I was hoping to do is rather than talking to you about utility supercomputing in theory, I wanted to actually bring together a group of people that are actually doing amazing work today and in years past by actually leveraging cloud to run HPC in a very short time frame. So we have folks from Johnson & Johnson, Pacific Life, Life Technologies, Hartford Life, and Novartis are all going to discuss their various actual use cases. We'll close with some Q&A, so if you don't mind, hold your questions until the very end of this talk. And then if we don't have enough time, we'll spill out into the hallway, and you're obviously welcome to stop by our booth and find out more there as well. Each of these speakers has basically 2 things in common. So first off, they're all doing research that fundamentally helps everybody in this room. So they're either building better medical devices or running the computations that help people to do this. They're managing risk. They're helping quantify genomes that hopefully will help push forward disease treatment. They're enabling folks to protect their retirement funds and earn consistent returns on them after years of labor, and also doing work that hopefully identifies drugs that can treat disease. So all of these areas are really fundamental. They're the things that are hopefully helping everybody in the world. And they also all come from organizations that are very large and have the capability to use any possible tool in their tool belt to solve problems. And each of these folks are using cloud essentially to run HPC to accelerate their science, accelerate their business in a fundamental way. So all of them are doing great things. And I would say that by self-sorting yourselves and coming to this session as opposed to all others, odds are that all of you can potentially do great things as well, or your organizations can. So the challenge I have for each of you is, as you're listening to each of these use cases, figure out the ones that actually relate to you or relate to the work that you do or the research that you do, and think if there are big questions that you could be asking, the million-hour questions that could potentially accelerate the way that you do business. And yeah, definitely ask about them at the end of the session. So with that in mind, let me introduce Kurt Prenger and Taylor Hamilton from J&J. They're going to talk to you a little bit about how they're using high-performance computing in the cloud to accelerate the work at Johnson & Johnson.
Really appreciate the introduction. So I'm Kurt Prenger, and this is Taylor Hamilton, and we work at Johnson & Johnson within the high-performance and scientific computing space. And before I get into the presentation itself, I'd like to talk a bit about how high-performance and cloud computing is really helping J&J enable science that we've never been able to do in the past. And I'll do this through one example. Within our pharmaceutical sector at J&J, there's a group called Model-Based Drug Development. And what they're in charge of is simulating clinical trials. And their ultimate goal is to minimize the time it would take to reach a statistically significant response to the answer, can we release this treatment or this drug to our patients safely and effectively? And how this is important is, for example, we recently released a drug called Zytiga, which is used for patients with late-stage prostate cancer. These patients don't necessarily have a lot of time left, and by getting through clinical trials more quickly and getting the treatment to our patients more quickly, they're able to extend their lives and enjoy more time with their families. So that's just one example. There are hundreds of scientific teams across J&J that have similar products and similar capabilities that can significantly impact the patients that use our products at Johnson & Johnson. So with that being said, I'm going to just talk in a general sense what kind of challenges our team faces when we deal with our scientific business partners, a solution that we're partnering with Cycle to implement that helps a large majority of these business partners. And then Taylor's going to talk about the architecture and the workflow of that solution. So J&J has the same old story that most enterprises do. We have a lot of scientific teams across the world, and they all have their own disparate internal clusters. These might be servers they've shoved under their desk or in a data closet somewhere, but they are disparate clusters that don't talk to each other, and they can't utilize the shared resources. This is okay on a daily basis when they're doing smaller jobs, but when they really want to run significant, impactful science, they don't have nearly enough resources to perform the jobs that they need to do. So they'll come to our group, and what we'll typically do, since we're not a software development company, we'll just come up with a homegrown solution that's a separate external system that will allow them to run their large simulations in the cloud utilizing cloud resources. This is a completely separate system, so IT needs to remain heavily involved with the entire product lifecycle of this in order to make sure that they're getting their jobs where they need to go. So what we did, we partnered with Cycle to implement the Submit Once technology. Now, Taylor's going to talk in more detail about how it works, but the main important benefits from this is the user is allowed to use the existing submission portal or command line utility that they use to submit their jobs, and Submit Once does all the work on the back end as to whether or not these jobs should be submitted to their internal clusters that are already existing or burst out into the cloud if they are larger jobs that will need a lot more compute resources. This means that IT does not need to remain heavily involved because the administration of the system is the exact same as they've always been doing with their submission tools. So this is a win-win for both IT and our scientific partners. So I'm going to hand it over to Taylor, who's going to talk about how the Submit Once technology actually works.
Thanks, Kurt. So just a quick high-level overview of what this architecture looks like. It starts at the bottom left with the client submitting their jobs. As Kurt mentioned, this can happen either through a command line interface or a submission portal whatever it is that they had that already existed before implementing this cycle solution remains in place. The front end really didn't change. Jobs head down to a broker, the cycle server software that's running submit once technology. And then from there, we actually have some customers who don't have a local grid in place already. And so the jobs just head straight out to the cloud where we have a cluster set up for them. Or if they do have a local grid, then jobs will head there first until that grid fills up. And so as we get to times of high usage, maybe an FDA submission deadline, or as we talked about, some new science that hasn't been done before that really requires compute power that we don't have locally, then those jobs can get routed out to the cloud instead of to the local grid. And all of this happens as transparently to the user as they would like it to be. So the decision-making process that's happening in the submit once setup, this is, again, pretty high level. The actual technology is a little bit, has more inputs that it can use. It takes into account things like the time that it takes to spin up a cluster in the cloud, the time that it would take to transfer data in and out of that cluster, and it lets users specify whether they want a job to run locally or remotely if they want to be able to make that specification. But lacking that, the user can submit a job and say, as they do a submission, is there a deadline, a time that I'd like to have this job finished by? And so submit once will take a look at that deadline and estimated runtimes of each of the job's components, and it'll say, can I run this job on the internal cluster with the resources that are available now? If so, the job will route internal, and if not, then at least some piece of that job is going to go external. If the user doesn't specify a requested completion time, then instead the submit once technology will take a look and see if the job has enough space on the internal cluster to run internally. Again, if so, internal, and if not, then at least some piece external. So for this at least some piece, what we mean here is we do have some users that have embarrassingly parallel jobs, and in their case, jobs can actually get split up. And so if they submit a batch job and it can be split up, then submit once is smart enough to split it up. It will take whatever it can to fill up the internal cluster and then route the rest externally so that we make sure to maximize the use of the resources we already do have, as well as minimize the time that it takes to actually finish the job. So that's our walkthrough. We've really found that our partnership with Cycle, our use of submit once has been great for the HPC team at Johnson & Johnson, as well as the business partners that we've been supporting. And as Kurt has mentioned, we can really draw a pretty clear line from the work that we do to the people that we affect and the lives that we help out. So it's been a really great experience for us. We'd love to talk with you more about it afterwards if you want to come find us or in the Q&A session. So with that, let me introduce David Chang, the Assistant Vice President of Pacific Life, and he'll come share his story with you. Thanks.
Well, it's a pleasure being here today. My name is David Chang with Pacific Life Insurance Company. I lead up the risk management team for our variable annuities business, so naturally my discussion today will focus on the VA space. In the next few minutes, I'd like to talk briefly about our ever-expanding needs for computing capacity, covering really three broad areas. Why do we have all these computing needs? What are we doing about them today? And what's the path forward? So why do we need all this computing capacity? Well, our products are very complex. For those of you familiar with capital markets, variable annuity guarantees are some of the most exotic, complex derivatives out there. Their payoff profile depend on many variables, and they're path dependent. So, and what I mean by that is, let's say the market go from point A to point B. Depending on how you get from point A to point B, you get a very different payoff for those guarantees. So, with those path dependency, there aren't really any closed form solutions to value those liabilities. And therefore, in order for us to do evaluation, Monte Carlo simulations are required, and that's really where the this computing capacity requirement come from. From a regulatory standpoint, the regulators want to make sure the liabilities are properly reserved for to pay those guarantees from a policyholder standpoint. So with all the product innovation in recent years, the traditional method in setting reserves for life insurance products are just not sufficient. So in recent years, there have been a lot of new regulations and that have been introduced and will continue to evolve in the near future. And all of those would rely with heavier reliance on stochastic analysis. So definitely from a regulatory standpoint, there will be more need for computing. Now from a risk management and hedging standpoint, we definitely have a lot of need for stochastic analysis and computing capacity. Why is that? Well, we care not only about the value of our liability, but we also care about their sensitivity so we can properly hedge for them. So just to give you an example, let's say we have a product that has a value that is dependent on 5 market indices. And it's also dependent on the curve of interest rate, the term structure. So even without taking into account how interest rates move, we need to know what our liabilities will look like if individual asset classes move or if they move concurrently. And what if they move in different directions? What if they move by different amounts? And what if they move in combination with interest rate move and in combination with volatility move? So all of those are things that we need to understand, and we need to do simulations to understand their value so we can properly hedge for those. So all of that, it's just kind of, I call this insatiable need for computing capacity. And by the way, for a lot of the financial reporting, you probably heard quarterly reporting for a lot of companies. From hedging, we actually need to do this calculation much more frequently. For example, the market can change from day to day. So any point in time you do a simulation, the very next moment, your liability have changed. So really, to have a very robust risk management process, you need to refresh this calculation as frequently as possible so you can capture what's actually happening in the marketplace. Next slide, just to give you, or actually a couple slides, just to give you some illustrative example on the type of calculation that we have to perform. This slide here illustrates for a single contract for one single path. For the sake of illustration, let's call this a 30-year projection, the horizontal line there. And we project out what the account value will be over that 30-year time horizon. That's the blue line. And we also project out what our guarantee value will be over that 30-year time horizon. And that guarantee value is represented by the orange line. And at the time of maturity for this guarantee, we calculate the difference, and that's the claim that the insurance company have to pay. And basically, for that scenario, we will calculate a present value. So that represents the value of the guarantee for that scenario. Simple, right? Now, in order to really understand or capture the value of that guarantee, you need to run that simulation thousands of times just to capture the fair value for that one single contract. So, thank you. So do that 1,000 times or 5,000 times, and for a typical insurance company, variable annuities block, 100,000, 500,000, 1 million contracts, it adds up. So that's a lot of calculation just to calculate the value of that guarantee. And remember I talked about for hedging, we need to know all the sensitivities. All those combinations and things start to multiply. And very quickly, I lose track of what is a million, billion, trillion, or I need to look up dictionaries to figure out what the words are now. So that's just, that last slide is capture a single contract, single scenario calculation for a single path. Now, there's a lot of nested stochastic needs that we have, and a lot of that is coming from regulatory requirements. So this next slide gives you a illustrative example. So for reserve statutory requirement, let's say you have to run 1,000 scenarios. Each scenario across 300, 16-month time step, monthly time steps. So basically, at the end of each time step, you need to calculate the value of the guarantee, and you need to calculate their sensitivity so you can incorporate hedging within that reserve calculation. So as you can see, at each node, so let's just look at the top blue line. The first node at time step 1, we need to stop. We need to do 7 option value calculation. Each one of those, 1,000 paths, as we saw from the last slide. And we need to do that 360 times for that one path. And we need to do that 1,000 times. And this is, again, just for one single contract. And again, for some insurance company, you got 500,000 contracts. So 2.5 billion inner path for a single contract, multiply that by, 500 million, adds up. And I haven't even talked about triple necessary stochastic yet, which often is what's needed if you want to do some simulation and understand your exposure over time. So for example, what we've talked about, the 2.5 billion times 500 million, if we want to do a 5-year monthly projection over, just say 10 stress scenarios, you multiply that by 10, you multiply by 60 monthly time step. Again, I'm an actuary, but I lose track of what that number adds up to. So, anyways, the idea here is just to give you a sense on the amount of calculation that we need to do to manage the VA business. So, what are we doing today? Well, we take a more of an integrated approach, take advantage of both on-premise infrastructure as well as cloud. They're really designed with different intent in mind. For on-premise, that's really our primary computing resources for a lot of the steady state computing needs that we have, the ones that we know we're going to have more of a constant usage and not a lot of idle time. And for cloud, it's a good companion where we can use that as more of a contingent environment. If we have disaster recovery, we need to, our on-premise environment is just not available, or if, we have some, extra analysis that we need to do that we just can't fit that into our existing capacity, we can leverage, those on-demand resources that the cloud offers. So really, it's a consideration based on your business needs. Some of the things I listed down on the bottom of the slide, the idle time. If you expect a lot of idle time beyond your peak demand, you probably want to consider more of a cloud. So where you're not just having your resources sitting there, not doing anything, and collecting dust. And also for any on-demand or on-premise resources, you have to maintain them. You have to have your staff, do all the patching and so on and so forth. So those are just some of the considerations in terms of integrating on-demand versus cloud computing capacity. So path forward, again, there's just a lot of computing capacity needs that we have for the variable annuities business, and that will only grow. It's not going to slow. So some of the things that's been done within the industry, how can we model our liability more efficiently? There are working groups within the Society of Actuaries and the Academy, American Academy of Actuaries that focus on that. So that's certainly something that's being looked at. Maybe some broader adoption of the newer technologies. I know some companies do leverage the powerful computational capacity from GPU, but it's not broadly adopted yet. So maybe more software firms adopting that. And certainly further innovations. What else is out there? And definitely, working closely from the business side, working with IT professionals to determine what are things that we can do to address these needs that we have. And certainly, everybody here probably have some really great ideas. What do you think we can do to address this computational need? So with that, I'd like to introduce Amitabh from Life Technologies.
Hi, my name is Amitabh Shukla. I manage one of the software engineering teams at Life Technology. Life is, I'm going the wrong way over here. All right. So Life is a tools provider company providing tools in life sciences space. We have roughly about 10,000 people, and we have 50,000 products, all kinds of products, from reagents to sequencing instruments. And we are betting a lot on sequencing instrument, and this is where we see a lot of growth coming in future, right? So, in 2000, we spent roughly $100 million to sequence one human genome, right? And we have come far, far away now. We can sequence a genome in less than 10 days for $10,000 today, roughly around $10,000. And our goal is to get to $1,000 genome. And we expect to achieve $1,000 genome by end of 2013, for sure, right? That's where we are heading to. So what we are providing is a mechanism by which you can sequence, depending on your need, whatever throughput you want, right? So if you want to sequence 10 gigabytes worth of genome, that there are different products which you can use, and you can sequence 10 gigabytes, or you can go up to 100 gigabases if you need to. So if you look at the graph on the right-hand side, the price is going down, the data is growing. We are generating lots and lots of data, right? And we believe that a person is going to get sequenced more than one time in their lifetime, at least, right, in near future. In order for you to get diagnosed, or in order for you to understand what you're going through, you'll get sequenced more than once. And if depending on what type of sequencing you're doing, you can generate anywhere from 700 gigabytes to 1 terabyte worth of data if you're doing whole genome sequencing. If you're doing panel sequencing, you're generating less data. Less data for us is roughly few gigabytes, 10 to 12 gigabytes. If you look at genome, the meaningful portion of genome is exome, where exome is the area where there are all the genes. It's roughly 1% of the genome. If you want to do exome analysis, you roughly generate 45 gigabytes worth of data. So data is coming, data is here, right? We are going to be producing lots and lots of data, and data is going to be there, and we want to make sure that people who are going to be using data, these are scientists and molecular biologists and medical pathologists, right? They can get access to data faster, cheaper, better, right? And they should be able to collaborate, and we want to be able to provide a platform where third-party solutions can come and interact with what we are trying to provide to them. Right. So Life Technology is using, with help of Cycle and AWS, we have built a software solution called Ion Reporter software. And in this particular workflow, we are showing what is the workflow from sequencing instrument all the way to cloud and people sharing data, right? So there are two instruments on the left-hand side. One is PGM, the other is Proton. PGM is small instrument, produces less data. Proton is bigger instrument, produces more data. It's all based on semiconductor-based sequencing technology, no lights, no optics over here. So we have a chip. The chip produces data. We measure voltages and generate base call from it. Right. So the problem is there is lots of data which is being generated, and the data needs to move to cloud, right? And imagine, right, one chip can produce anywhere from 10 gigabytes up to terabyte worth of data over a period of time. It's not producing all at once. And what we need to do is make sure that we move the data up to cloud, we analyze the data, and analyze the data basically means that we have to go through the process of taking voltages, converting to base reads, mapping it, producing variants, what has gone wrong in the data, right? The areas which you are interested in, provide a good user interface for people to go figure things out, looking at large number of data. This is a basic data reduction problem. You have lots of data, you want to reduce the data, and even when you reduce the data, if you're looking at whole genome, reduction basically leads to 2 million distinct calls, right? 2 million variants can be detected. So there's lots of data for a given sample which you are generating, and you want to make sure that you use technology which enables you to bring that data faster in front of the user and yet provide a quick, very good user interface for it. Right. So how do we use AWS, right? So our solution basically has two types of needs, right? One is fixed asset needs, and we have application server, traditional web application, which is serving up the pages. We have data upload servers. We have farms of data upload servers. These are basically bringing data in from instrument into our application, right? So somebody goes, sets up, puts a chip in there, puts their reagent, clicks the button. That sequencing run is happening, data gets uploading. When the data is uploaded, it gets to a shared file storage, a pipeline is run, and when we're running the pipeline, we spin up hundreds to thousands of nodes to process the data. We want to make sure that we can analyze data as fast as possible, right? And this is where we are using CC2 and using Cycle Cloud Solution to make sure that we can spin up nodes, take the data to the nodes, use Hadoop kind of distributed infrastructure to break down the problem, spin up lots of nodes, produce and reduce data from terabytes to 2 million reads. Basically, that's what we're trying to do, right? So we're using all kinds of technologies over here. We use NoSQL technology to make sure that the information which you're seeing on the right-hand side in the picture is presented to them for the area where there may be changes in their genome, right? For storage, we are using EBS for primary storage, S3 to archive data. We are also looking into using Glacier for archival solutions just because of the cost reasons, right? We found cloud deployment easy to use, right? It simplifies the user experience for people. Our business model is pay-as-you-go basis. It's tied with chip. If you buy a chip from us, you have an option to buy, analysis. And for a small analysis where data is 10 gigabytes, it's roughly, anywhere between $5 to $10 per analysis. So if you buy more chips, you're running more experiment. You get the data over there. You analyze the data. You generate the report, and we are enabling also our partners. We know that we cannot do all the work ourselves, all the scientific work which we need to do. We have to bring people from outside. We have to collaborate with other folks to bring their solution into our fold. And we are using cloud deployment and the infrastructure behind the scene with a set of APIs which we are building for our partners to build solution for us which can be deployed on the cloud environment. And we are hiring. Right. With that, I'd like to introduce Robert from Risk Management Technology.
Thanks, Amitav. Hi, my name is Bob Nordland, and I'm from the Hartford. I run Risk Management Technology. A little bit about our company. We're also in the insurance business, big surprise. We're founded in 1810. We're a multi-line insurance company. I'm sure either some of you or some of your parents, probably your parents, might have some coverage with us because we have a big affiliation with AARP. But primarily what I'm here to talk about is risk management, in particular market risk management. That's our primary use case for all of our high-performance computing. So why does a 200-year-old company need HPC computing? Well, I think as David pointed out, it's these variable annuities. Variable annuities are complex derivatives. They're very difficult to model. It's not something as simple as plugging in Black-Scholes with your dates and some volatility, and then you're all set and good to go, and you run it on your PC and you're good. So we've been, for the last 10 years, modeling our VAs on a grid. And just for a little point of reference, variable annuity is really just a mutual fund wrapped in like a life insurance policy. I'm not sure if that's a good characterization, but that's what I'll go with. But the main use case for modeling these is because we need to implement a hedging program. And basically a hedge is coming up with an asset portfolio that kind of counteracts how the liabilities move, and that's how we manage those liabilities. And also, as David was pointing out in Pac Life, is we do offer the investment guarantees that we had put on top as a rider on our variable annuities. So that means that when the market moved big, a lot of our customers in 2008 were pretty happy because they were deep in our benefit, and we guaranteed that they didn't lose any of their money. And because of the hedging program that we have in place and the high performance computing that we had to model that, we were able to have a responsive hedge that ended up allowing us to continue on our 200 years of honoring our promises. So what kind of things do we run on our cluster? Again, Monte Carlo simulations of assets and liabilities. For the most part, it's on the VA side. And since these are complicated and they do have long time horizons, there's a lot of different points that need to be calculated over time. And we're modeling things in terms of, sensitivities to interest rates, sensitivities to volatility, how do they move with FX. These are, global financial instruments that a lot of people really rely on. And it's a very critical thing for us to make sure we're accurate in how we model these and making sure that we can cover our obligations for our regulators, to our shareholders, to our customers. So it's a very complex process. It's important. It's millions of policies. I think we're one of the larger VA providers in the market. We have 2.5 million or so policies in there, millions and millions of scenarios, and trillions of calculations. So I said that we've been running for about 10 years, and we do have a fairly large internal cluster. This is I think we're at around 7,000 cores that we have dedicated to doing our VA processing. We've recently introduced CUDA into the mix as well. We're running on top of Condor, and we have been since we started back in 2003. For those of you not familiar with Condor, Condor is from the University of Wisconsin. I think it's been around since like 1985. And we're actually one of probably Cycle's earlier customers, and we've been using Cycle Server to manage our infrastructure and help make it easier for our users to use the grid. Who's using it? Actuaries and quants. They've kind of grown up with our grid, so they're very familiar with the concepts of parallel computing. Everything that they do, they think of in terms of those small nodes. It's a blessing and a curse. The blessing being that it's easy to talk to them about how big is your run, how long is it going to take to run, how many resources is it going to occupy. But the bad part about it is that they're very good at extrapolating. And they immediately say that, if it takes 3.5 hours on 5,000 cores, then it's only 3.5 hours on 50,000 cores. Where's my 50,000 cores? The big challenge in working with them is the fact that they don't always see that there's technical hurdles into scaling horizontally as large as you can. In fact, if I think it's less of a pressure for them to say, I can't justify adding more. I mean, they have access to the money because these are very important things for the company. So it's not a question of finance. I have to put on my IT hat and balance off how they can effectively use IT. I can't just take their blank check and go fill up our data centers. So what brings us to the cloud? Well, two major points of pressure for me. One is just the standard IT reduce cost, reduce unit of what our compute costs are. And then the next is scale. And I find the scale thing more interesting. We do have ongoing models that we can run that simulate what is our cost internally versus what are the costs in AWS. So we have a good handle on that. We know where we have that point at which we pull the trigger and move over into Amazon. And we can do that because we've kind of kept our workloads as simple as possible, so we can seamlessly switch into the cloud or onto our internal servers. It really doesn't make much of a difference with the type of workloads we run. But as far as scale, the demand for large-scale simulations for different strategy work, where we got stochastic on stochastic on stochastic now, we're looking at workloads on the order of 500 times larger than we run on a nightly basis. So when we talk about how big is big, the nightly production process that we run keeps our grid busy, 5,000 cores from 10 to 12 hours. If we look at simulations that we're looking to do now, we're looking at 2.5 million core hours. And that run is going to need to be completed over a weekend. If you look at the amount of compute that's necessary in doing that, it's going to require a cluster of around 50,000 cores in order to accomplish that. We're confident in our workloads ability to scale. We're also confident in the fact that Cycle Server has done this before with Schrodinger. We know Amazon can scale to that level, and we know that we can get this done. We've got our own software, so we don't have any licensing issues, which makes things much easier to accomplish, because as anyone who's worked with cloud and proprietary software, then licensing can be a challenge. So our cloud strategy is, unlike Johnson & Johnson, at this point we're not spilling over into the cloud. We're not supplementing our internal capacity. We're looking to run large autonomous units of work out in the cloud as kind of one-off processing jobs. That's going to be our model, at least going in through the next year. We're always looking at the price, performance, scalability, availability, benchmarking things against what we currently have in-house and what we can count on, and just being able to have that smart decision on now it makes sense to move everything over there. At this point, it's not, the financial case hasn't been made yet to go off our internal stuff, but as far as the scale, we have no other option other than moving out to Amazon. So what's next? Some of the things that tend to get ignored are when you look at just moving everything over to an expense-based model, it's slightly different from a financial perspective. It's not as easy to budget. It's not as easy to predict how much compute cost is going to be used next year. Do the people that are submitting work have the authorization to initiate a job that may result in tens of thousands of dollars in compute time? What kind of governance can you put on to make sure that they've done their due diligence to make sure that they're going to get value out of that? We also have to take a look at the workloads themselves to make sure that there's not personally identifiable information in there. There's some things that need to be tightened up. Disaster recovery, we do have 2 data centers, but we are looking at Amazon as a way to maybe make that a little easier, maybe ways to fail over and also pick up some additional capacity. Application development has to go hand in hand with looking at the cloud too, because we want to take advantage of spot instances, and we want to make sure that we can plan for doing very small units of work to kind of slide in and maybe cheat the economics a little bit. So in general, observe and refine our strategy, but it's definitely part of our strategy. Closing thoughts is we're keeping everything simple. Our workload, even though we've scaled from 2003, maybe 36 cores that were on task, maybe 500 jobs, to millions in jobs on tens of thousands of processors. Nothing has really changed so much in the application architecture. We are hiring, as I'm sure a lot of people are, so if anyone feels that some of this is interesting and might apply, I encourage you to come talk to me.
So with that, we wanted to close. I don't know, Lisa, if we have time. We do not have time for questions right now. So instead, I think what we'll do is pull over after the session. We'll also be out in the hallway. I'd like to thank everyone that talked today: Taylor, Kurt, David, Amitabh, Bob, and Steve for coming and talking. If you want any more information about any of these individual areas, we do have a lot on our blog. We are hiring, and we are obviously available also at the booth once the in the hallway session is done. So thank you all. I hope some of these helped you see areas where you can take advantage of either small or very large scale computation to be able to speed, ideally, your ability to run science and do your business. And with that, we'll close the session. Thank you very much.